Mixing, not mixing, mixing, not mixing, that's still confusing. So you just got lost with the mix thing, forget about it for now, you don't need mixes here. Okay, so that's just confusing me more. Thank you, Michal. I mean, they'll be useful for QAUA though. So when it comes to measurements in various bases, this was definitely the most difficult part for me to understand. It kind of makes sense, but I don't. It kind of makes sense. Let's put it this way. So, um, you've got a Hamiltonian that is expressed in terms of uh, some computational basis. Mm, and because you're doing stuff along those bases, then it makes sense you need to measure them in a certain way, somehow. Uh, I'm not saying it doesn't make sense. I think it makes sense. It just it's one of those things that just makes sense, but you don't really necessarily understand why. Um, and 3 months. Okay. Yeah. I mean, take your time. That's a good. Oh gosh. Yeah. So it's a good piece. It helped me definitely click a couple things here and there. Just wanted to do that short video, second part, where because I had read that before. I think it was in. I think it had to be in David Kopchik's VQE post. I think he did a similar one where he talks about, so exactly that's this one. So also expectation value, blah blah blah, implementation from preliminaries, ansatz. There's some stuff in Python as well. So he's using similar concept like me, how, or the other way around. Expectation value. Um, Okay, but let's have a function of an expectation value. The measurement of the qubits in Python is either made in state 0 or 1, so this is not straightforward to calculate the expectation values. However, there's a simple trick. Firstly, let's remind ourselves the measurement project is presented in this post. Because I think that's what it means to measure the expectation value of that Hamiltonian is so is that so what I think basically, so we talk about mixers and we talk about mixers and cost Hamiltonians in QANA, and I think that is mostly what Jack talks about, and the Google team talk about this as well. When we talk about QAOA, I hear basically VQE in this case, based on David Kopchik's blog post and Michał's blog post. It's like pick whatever random thing you want as a model, as an ansatz, right? So whatever ansatz. Um, so, and then measure the expectation value of the Hamiltonian. So the Hamiltonian here is basically your mixer. It will be the equivalent, because what you're saying is measure it, or use the Hamiltonian's structure to measure, because that's what's kind of giving you the evolution per se of the energy kind of thing. You know what I mean? So there's no you're not implicitly exploiting a structure of the problem, whereas in QAOA you're doing so. In QAOA you're following a particular ansatz style, which basically already kind of has that Hamilton. It already kind of is shaped in the Hamiltonian way. because, and I think that's kind of the difference. Correct me if I'm wrong, but I think that's really the way those concepts relate to each other. It's just um, mixer. I feel that's because the ansatz, right, is really and then in Cirque's in Cirque's read the docs, basically they talk about an ansatz strategy is strategy QAOA. There's a lot of frame defining variation ansatz. Here we'll go with the version of QAOA strategy and define an ansatz related to the problem we're trying to solve. And so here, the ansatz is really it's really the Hamiltonian, right? Whereas what VQE in general says is don't kill yourself with an ansatz that has anything to do with the problem at hand. Just try to get something that allows you to explore the space in a way that it's kind of balanced. It's not too much and it's not too less. And then the actual the expectation value you got to measure by understanding the structure of the Hamiltonian. So that's I think those are not two contradicting things or opposite or whatever. It's just different namings for the same concept. So one on the VQE side, on the pure VQE is basically saying design an ansatz that allows you to explore space, and then measure against the Hamiltonian structure. And what pure QAOA is saying is your ansatz really is that it's design an ansatz that is basically the structure of your problem. So use the Hamiltonian to do that. And then you've got that mixer in it that I don't really yet grasp. But let's close these first, and then we'll make another video on finishing up also Jack Theron's notebook, and because I feel I've been jumping and getting distracted, and these are all related topics, but I've been hopping around those things, and I just want to kind of get it closed at some point. Good. Now that I've ranted a little bit about it, so let's go back here. So do we really what is in there? So I didn't read the hybrid approach as mentioned earlier in VQE. The hybrid quantum classical algorithm means we don't perform all the computation on a quantum computer. It was classical 1-2. Remember the answer has a lot of parameters, right? The problem is that we don't know which parameters are good and which ones are crappy. So what do we start to learn now? We treat it as a regular optimization problem. Usually we start with a random set of parameters which corresponds to a random state. We use is not a random state chosen from the set of all possible states, but random state chosen from the set of all possible states that we can get with a given ansatz. Yeah. We perform measurements so that we know the corresponding energy. We also use the term expectation value. Then we slightly change the parameters, and if the new energy value is lower, it means that we're moving into a good direction. So the next iteration will further increase those parameters and having okay. Yeah. You're probably gonna read better this way. The optimization strategy described is pretty trivial and is good only as an example. Choosing a optimization method for a problem, decide whether you'll succeed or not is pretty difficult. And also with bullets here, you can choose from a range of methods like SGD, BFGS, or Nelda meat method. But that's not the point here, I guess. An incomplete list. What a GPU does, given a set of parameters, a set of measurements. Okay, yeah. So it's a quantum computer for one thing only, to get the energy value of the given set of parameters, and everything else, the whole optimization part happens in a regular computer. We know that. Why is it appropriate for NIST devices? Noisy, blah blah blah. This video and paper, not perfect million qubit devices that are needed to run the famous Shor's or Grover's algorithms, but rather several qubit prototypes. Main disadvantages on these: there's a lot of noise, don't live long, don't have too many qubits. Translates to a pretty clear set of restrictions in a quantum circuit. You can only use n operations per qubit, so-called circuit depth. You can't assume everything will go according to plan and there will be no errors along the way. Even if there are errors, you should still get a reasonable, though not perfect answer. We call this robustness. Obviously, you can use more qubits than you have. You can't. Yeah? So why exactly VQ is a sensible proposition for niche devices? It's pretty flexible when it comes to circuit depths. You can make some trade-offs. You can use pretty simple ansatz if you want to keep a circuit very shallow. But once you have the machine which allows you to deepen circuits, you can use more sophisticated ansatzes. VQE has been shown to be somewhat resistant to noise, and the present noise up to some levels correct results. Some even claim to pinch a noise might help with the transition process because it helps to escape local minima. There are some practical problems that do not require a lot of qubits. For example, one example can be nitrogen fixation, important industrial process. Okay, example. There's an example. I'd like to know how the VQE works is a link to the Jupyter notebook with an example in Well, it's not sophisticated, but it follows exactly the steps you have seen here already. I encourage you to play with it, see how it works, try to improve it, write your own proper version of VQE, and check if it gives you the same results as different open source implementations. And if you do, make sure you let me know. I also think now you have finally all the pieces to appreciate the following picture from the original VQE paper. It shows the overview of the whole algorithm. You can read quantum state preparation as ansatz, quantum module as adding rotations to enable measurements in the right basis. Quantum state preparation, quantum module 1, 2, 3, 4. Okay, yeah, okay, I get it. So the different parts of your Hamiltonian. Adjust the parameters for the next input state. Closing notes. I hope. Yeah, I've enjoyed this blog post, Michał. It was more technical than my usual running, so please let me know if you found it useful. It's difficult to get something right on spot for all the audiences, And some people, they just want to stay at the hype level and, talk about how many scary things can and will quantum computers do, but once you get technical, actually it helps to for people to actually spend the time if they really care. I always tend to go much deeper into the math here, but then this would end up being twice as long. For the curious readers, I really recommend digging deeper. Provide some resources in the text if you have any feedback. Let me know. Huge thanks to all these people. Man, that's a lot of people. Also thanks to the Quantum Circuit and QT teams for creating great tools I use for drawing circuits in blocks here accordingly. Quantum Circuit. Is this the... Honestly, I think you do better with Quirk. All you've done is use it for those things here. And actually doesn't help you even because you have to add those extra lines here explaining the angles and stuff. You could just have those angles in the pictures directly. Doesn't this allow you to do that? I think I had an account there at some point. Learn Quantum, was it Learn Quantum? Oh yeah, that works. New project. Test. Oh, test. Test already exists. So if I do that, can I specify the degree of rotation? I can't. Let's do new page. Can do that. Seems like I can't parameterize. So I gotta go new gate, QFT, create gate from the circuit, QFT converts from random supremacy circuit. It's a composite gate. So you click and you get it here. That's quite nice. But still, okay, whatever. Anyways, let's go and check out the PyQuil stuff. See if there's something to play with. Whom one. Hybrid approach. Example. Good. So this is a notebook which is supplemented to my blog post about VQE. It's not a VQE tutorial, rather an illustration and invitation for the reader to explore the concept described in the blog post on their own. This calculates what's the expectation value of the quantum state produced by a given program. Expectation value. So wave function simulator results, zero wave function program prop dictionary, get outcome props. Then for each key value in the prop dictionary, result equals value times the key. What? Okay. Is it okay? So is this basically kind of doing this? So the term wave function, get the items, get the outcome props. But wasn't the expectation value the actual average? Is that the key is used as just a probability? Arbitrary value of theta, some ansatz. Circuit 1 is the ansatz, circuit 2 is the following program and ansatz, and then that rotation. Here account for the constants. Term 1 value is 2 times the expectation value of circuit 1. Term 2 value, it's the expectation value of circuit 2. Term 3 value is 1. The energy estimate is this. Okay, no, the expectation value. And okay, so 2. Energy estimates. Theta values. NP Linspace. So that's generating. That's basically generating already a set of theta values to go through. So it's not really doing any optimization, just going through a set of values like Jack does as well, I think. At least in his original blog post. Ansatz program, circuit ansatz, circuit 2 ansatz plus program, term 1, term value. So we're doing everything. So you're just putting those things in there. Energy estimate. Append energy estimates, append energy estimates, and then plot this. Plot values, x, y. Plot values, theta values, term 1 list, term 1. Plot values, term 2 list, theta values. Okay, so plot values, theta values, term 3. So you're plotting for each of the theta values what is the result of the term, the result of each of the terms of the Hamiltonian. These, and constant. The constant makes sense. And then the energy estimate is this, basically. And that's it. That's it. What's there to play with? What else could we play with in here? What's the expectation value of the quantum state produced by a given program? Wave function simulator. What is? I'm not familiar with PyQuil at all, so. The wave function simulator. Inspect the wave function of a quantum state prepared by your program. Okay, so it gives you access to the into simulator, so it gives you access to the probabilities. When running on the QPU or QVM, you would aggregate results anywhere from tens of trials to 100k plus that you can sample to get back a distribution. With the wave function simulator, you can look at the distribution without having to collect samples from your program. Ah, okay. But then you're cheating. This can be saved a lot of time for small programs. Let's walk through. Okay, so basically, so that's cheating, because that only works on simulators. But yeah, okay, it's because that's what I mean. You usually have to sample and then simply average out from all your samples. Whereas here is you're basically getting the expectation value. So the value, if I'm correct, if so the value, what is that? The probability. The value is the probability, right? So so if you would get the if you would have like 50% chance of measuring 1 and 50% chances of measuring 2, well, you got 1.5. Yeah, I guess that's the correct answer, isn't it? Isn't it? I think so, huh? 1.5. That's the expectation value. Okay. Yeah, it's not a big deal. You probably, but I mean, you probably have to change that anyway. So just so this would only work with the simulator, of course. If you're gonna try and run this against an actual QPU or like a quantum computer, you need to change that with actual sampling. So this means you would have to run the program like 100 times and then calculate the expectation. Just calculate the average of the outcomes you're measuring. That's it. But I think Jack does it this way already. But the rest is fairly straightforward in this notebook, I'd say. So the approach that's used here is just a list of theta values, which is created by this here. And I think Jack uses something similar. What is Linspace in NumPy? Linearly spaced vector, yeah. So what it does is probably it goes from 0 probably to 100 by jumping with the discrete intervals of 2 times pi. And is that what it does? Or something similar? Because it goes 0.25 pi, 0.5 pi, 0.75 pi, 1 pi. Okay. What is this 100 thing here? parameters. Start, stop. That's start and stop. So that's start 0, stop at 100, stop at 2 times pi. Okay, and do that in, I get it, and have 100 different, so you don't see that here, but you've got like 100 different samples in here. That's why it looks it looks kind of continuous, but it's really not. It's just 100 different, and then you plot that. Okay, get it. Get it. Other than that, it's just that. Yeah. Nothing else to play with here, I'd say. The ansatz you could change. Basically, does he mention different possible ansatz? Why doesn't this work properly recently? There is an ansatz. So that's the ansatz we're using. So you could try to make another ansatz where we have Rx and Ri and Ry, and then you have multiple parameters. See if that changes the see if that changes the actual outcome, basically the energy estimate. Here's just one thing, right? It's just one theta, one thing to optimize with theta in theta values. And what we need to do here is what we could change here is that program and make it like to have another gate with another angle, and then do sort of a nested loop. Yeah, but then how would you plot that? Because that plotting here happens against the theta values, and in this case we would have theta values and, say, I don't know, alpha values. So you're not really neatly be able to plot that. Energy estimates. Append energy estimates. Yeah. You would have to have a different plotting strategy for that. But maybe I'll do another quick video trying to play with this a little bit. See. I will try not to spend more than 15 minutes on that. We'll see. We'll try to do that. How can I do that? What's the easiest way to do that? Can I just download? No, I can't download that, and because I need definitely to have PyQuil installed for this to work out. So cool. Anyway, but that's it. So I'll do another video on that. I'll probably publish them at the same time, and then get that, just play around with the code a little bit, do a couple of examples, and yeah, we would have to plot for the different combinations of parameters, right? So you would get many more values in here. But then the energy estimate, I mean, I'm curious. I don't know. We can play. Yeah, let's do that. Come on, let's do that.